Well, another blast from the past. The first and, well, only multimeter I ever built. About 35 years ago. You may recognize the instruments. I have the same type of instruments built in the power supply. I did back then and revamped lately. Card link. And it's a interesting piece. I mean, obviously, you've got no switch, but a lot of plugs to get to your different ranges. There's a switch, and I have absolutely no idea what that does. You have a fuse holder. It's fused, of course, and the fuse is probably, well, in pieces, but it's holding on by a thread, and that's all what we need, isn't it? Kind of the intended purpose of a fuse. So, I'd say let's get it apart, but first we have a look on the different plugs here and what their purpose is. So, this is a typical German ground symbol back in the time, and interestingly, I have two grounds here. I have one for DC and I have one for AC, which is interesting. Then I have the ampere ranges from 4 ampere, 400 milli, 40 milli, 4 milli and 400 microamps. Then I have all, I guess, DC. Then I have DC volt ranges 440, 4 volts, 400 millivolts and 200 millivolts. And that's red probably because if I remember it right, the instrument has full scale at 200 millivolts across it. And then we have AC ranges, 400 volts, 40 volts, 4 volts, and another ground plug labeled A ground. Interesting. And 440 microamps. And you can probably read that, but this instrument has full scale at 40 microamps. So I guess these two are connected together and going directly, out of focus, through the instruments. Well, let's get it apart and maybe reverse engineer a little bit what this is all about. One screw is a little bit different. Whatever. And it should come apart quite easily. Ooh. And there's a piece of paper. A lot of German names. Interesting. I don't know, was that in here to keep that from wobbling? I will try. This is quite old and yellowed to get it apart later. But let's have a closer look at the innards. Well, on top you have the instrument, that's easy. We had that ominous switch, the fuse holder, and yeah, these were the two ground plugs. And then we have, let me see, yeah, these are the different amp ranges. Yeah. And yeah, lots of shunt resistors, and yeah, the highest range, the 4 amp range, a whole bundle of shunt resistors, 5% accuracy, so nothing to write home about. That was here the series resistors for the DC volt range, and here we have the series resistors for the AC volt ranges. Here's my second ground. Oh, my third ground. Remember, I have a DC ground, I have an AC ground, and I have an ampere ground. I don't get it. And as I suspected, these two plugs, 40 microamps and 200 millivolts, directly to the instruments. They are just, yeah, shorted together. Tell you what, I will try to reverse engineer that, and then we can maybe understand a little bit better what my intentions were back then. Oh, yeah, and for the DC voltage ranges, yeah, these are two. Can you see that? Yeah, plus, minus, yes, plus, minus, DC. These are two half bridge rectifiers. Okay, and maybe this piece of paper can give us a hint when this was actually built by me. Yeah, it's kind of brittle, and it's in German, and it looks, it looks like television program. Yeah, it looks definitely like television program, and it says Monday 9th of March, but on the top it says November 1181. Oh no, this is March. This is the 11th week of 1981. And 81, this would make the whole thing 2018, 37 years old. Yeah. And oh, and on the back side we have the circuit diagram in all its glory. Yeah. And it's dated the 5th of July 81. So yeah, 37 years and 3 months. Yeah, this is, I mean, I don't have to reverse engineer that because it's all here. So we have ground that goes to the negative of our instrument, and the instrument itself is fused. We already saw that. Then these are our DC ranges with yeah, decreasing or increasing series resistors. Yeah, you can read it yourself. Yeah. So this is 9 mega ohms plus 900 kilo plus 90 kilo plus 5 kilo. Whatever. The other side, the current range is a little bit more complicated. I guess that's where the second ground comes into play, the A or ampere current ground. Okay, I know how this works. So, for example, for the 4 ampere range, you go here in with your positive, so current flows from here to the normal ground. You have a drop here, a voltage drop across your shunt resistor, as you should have. And then I guess you have to bridge with an external wire to the second ground. So you can actually measure the voltage drop across the resistor through the instrument. Also, not too bad. If you don't want to use a switch, which is here, and it says, okay, that switch decouples the AC volt part from the rest. So if that switch is open, the AC part is decoupled from the whole thing. If the switch is closed, the AC part is connected. And I probably, if we go follow this down, I probably introduced the switch because I didn't want it, the bridge rectifier made up from the 2 half bridges to be connected parallel to the instrument when I'm measuring DC. Yeah, I guess that was the logic back then. Yeah, there's also a little trim pot here, probably to, I mean, if this is silicon diodes, you have a voltage drop of 1.2 volts across that thing, and that's enormous. So I guess that was introduced to, you know, level out the error over the full scale somehow a little. And yeah, there's the port directly connected to the bridge rectifier, and can I read the value? Yeah, 100K. Woo! Yeah, but then if you look at the series resistors here, 900K in parallel to 6.2 mega ohms, so a little less than 900K, and 18 and 18 makes 9 meg, and then 100K here. Yeah, makes sense in a way. Yeah. I mean, 37 years ago. I don't know how old I was back then. Maybe 15? Something like that. Yeah, and that's all. That's really all. Yeah, down here I have some data. Yeah, yeah, for the voltage ranges, you have input resistance of 25 kilo ohms per volt. So yeah, for the 4-volt range, that would translate to 100k input resistance, which is, yeah, the 5k here. Oh no, for the 4-volt, the 90k here, the 5k here, and the 5k of the instruments would make 100k. Yeah, not really a huge input impedance, but anyway, for the AC ranges, it's 18k per volts, and yeah, that's not too shabby. The input resistance for the ampere ranges is only 0.012 ohms per amps. So at the 400 milliampere range, it's 0.005. Not too shabby, huh? Oh, it's not that bad. Oh, and at the very bottom I have a warning. In German, of course, it says, warning. Device has no protective isolation. Don't touch when using at 400 volts. Okay. I guess because this is all quite brittle, I will make a copy of that and put it back into the instrument. And I will put that together again, and then we can play around with it a little bit. Let's try the 4-volt range first. I mean, yeah, the fuse looked a little bit worse for rear, but yeah, anyway. Let's get that up to 4 volts. Near enough, and yeah, it's not quite on 4 volts. So yeah, now it would be spot on 4 volts, and this would be 4.07. That's not too shabby. Okay, let's try the 40 volt range. And no, I won't try the 400 volt range. Sorry. I think I only can get up to 24 volts or maybe 25 volts. We will see. Oh, 22. Okay, then let's go for 20. Okay, spot on 20, and it says 20.12. So that's not too bad. Let's try the 400 millivolt range. So 4 volts and 400 millivolts. Sorry, and we are spot on for analog instrument. Let's try the 200 millivolts. And yeah, I added an extra pot to divide the voltage down in these low ranges. 200 millivolts, so full scale is 200 millivolts, and it's 197 millivolts. So yeah, I mean, the DC ranges are quite okay. So the input impedance, we are now down to 5K directly to the analog instrument. That's obviously not acceptable, but accuracy-wise, it's okay. Yeah, the 4 amp range, and this is the bridge I have to introduce here to that. Yeah, that's not ampere ground, that should be amperes current plus or something. It's totally shut. I guess the resistors are rusted or something. Yeah, let's try the 400 milliampere range next. Yeah, the 400 milliampere range is not half as bad. Yeah, there's probably some oxidation going on here on the plugs, and yeah, but it's stabilized. Yeah, 390, 400. So yeah, if you remember, some of these resistors inside there were 5% tolerance. So yeah, let's go down to the 40 milliamps. 40 milliamp range is almost spot on. 39.72. So nice. But yeah, okay. I wouldn't use that for measuring current. One thing I learned is you first disconnect that second ground or the bridge before you disconnect the connection carrying the current, because otherwise you will put quite a strain on the instrument, like so. First disconnect that, because otherwise, no, I won't risk it again, but if you do it the other way around, you blow the instrument. Okay, 4 milliamps. 4 milliamps is also not too shabby. I mean, 3.93. Remember, this is analog instruments. Yeah. Okay, 400 microamp, and yeah. Yeah. We probably know how this works out, but what I'm really interested in is the AC ranges. How good are they? And I'm not putting 230 volts mains AC in here, so I will get out a transformer and we try the low ranges from 40 volts, 4 volts, yeah, 40 volts and 4 volts. Yeah, the two lower ranges. Well, the 40 volt AC range is not too bad. I mean, yeah, if I look directly on that instrument, the voltage is slightly below 26 volts, and yeah, that one shows 26.13, but yeah, it's really good. Yeah, one big advantage about using analog instruments for AC measurements, they are always true RMS. Yeah, you don't need no fancy calculations and electronics inside a multimeter if you use an analog instrument, because yeah, they directly measure the physical effect, in this case the magnetic force induced by the current, and the current is induced by the voltage. And true RMS definition is it's the voltage that causes the same physical effect or power in that case like the same DC voltage. And so yeah, analog instruments are by nature true RMS. So yeah, I built a true RMS instrument back then. Yeah, let's try the 4 volt range. And yeah, I don't have great hopes for that one. Yeah, the 4 volt range and yeah, that's total bullshit. I mean, 4 volts and in fact it's 1.37, 1.38. Yeah, and yeah, you see I'm using the other input here too. Interesting in effect. I mean, of course, I can switch it off completely. That's one thing. But the other thing is if I put it into... that doesn't look good. Huh. Anyway, let's leave it at that. Yeah, the circuit diagram is back in the case. I have no idea why that worked. Okay, yeah, that was it. My first self-built multimeter 37 years ago. True RMS, but otherwise, by today's standards, total crap. Bye.